Now, the last thing I want to discuss for basicity is of aniline. Here's aniline. It is a primary amine, and so of course we have that lone pair that can be donated, so aniline can act as a base. Now, if you remember the numbers for ammonia, the Kb for ammonia 1.8 times 10 to the minus 5, the Kb for aniline 7.4 times 10 to the minus 10. It is a ridiculously weak base compared to methylamine or ammonia. In other words, sticking on this phenyl group here really makes it a much weaker base. Well, why is that? Well, because that lone pair is delocalized. Remember that the basicity of this nitrogen is associated with donating that lone pair. And if you think back to what we discussed when we're thinking of the structure of aniline, this lone pair is delocalized within this big pi cloud. If it's delocalized within this big pi cloud, it's not going to be available for the nitrogen to donate it. So aniline is a much weaker base than ammonia is. Now, the properties of this aromatic ring actually lend itself to very significant changes in the basicity of this nitrogen when you start throwing in some extra groups there. I'm not going to dwell on it here. I might come back and do a more significant extension topic on it, but the sensitivity of aniline and substituted anilines in terms of their basicity is something that can be used extensively to track the physical properties of different compounds. But just to give you a taster for it, let's stick a methyl group down there on the aniline, or we'll stick a trifluoromethyl, or we'll stick a nitro group there. Now, when we put the methyl group there, the Kb goes 1.9 times 10 to the minus 9, bigger than 7.4 times 10 to the minus 10. So putting a methyl group there makes it a stronger base. Putting the trifluoromethyl group there makes it a much weaker base. Look at that. It goes from 7.4 times 10 to the minus 10 to 2.82 times 10 to the minus 12. Really weakens it. And then a nitro group there, the Kb is 1 times 10 to the minus 13. Now remember, water's 1 times 10 to the minus 14. So this is such a weak base, it's hardly a base at all. So look at the massive differences between sticking a methyl group on there, 1.2 times 10 to the minus 9, and sticking a nitro group. That's a change of about a factor of 10,000. That's what I meant by saying that these K values are so sensitive. Now, can we again explain why this is? Well, a methyl group has a positive inductive effect. It pushes electrons into the ring, which means that the nitrogen doesn't need to share its electrons nearly as much. So pushing electrons in there makes the nitrogen lone pair a little bit more accessible. Not very much. I mean, it's still a really weak base, but the lone pair here in this with a methyl group at the 4 position is a stronger base than aniline because it's easier for the nitrogen to donate those electrons. However, CF3 and NO2 both have significantly minus inductive effects. Here you've got 3 fluorines sucking electrons away from the ring. Here you've got a nitrogen and 2 oxygens sucking electrons away from the ring. As they suck electrons away from the ring, that means the ring is going to hold on even more to the nitrogen's electrons. If that ring's holding on to those nitrogen electrons even more, harder for the nitrogen to donate those electrons. Thus it is a weaker base. Basicity of aniline, the weakness of it and the sensitivity of it make it an extremely important species in studying different reactivities. And as I say, we might get onto that in a later extension topic.